Okay, welcome everyone. How many of you are here first time? Oh, quite a lot. Okay. The theme we are following is from CS 231N, Stanford Deep Learning Computer Vision for Deep Learning for Computer Vision. So that class expects you to have some understanding of machine learning, basics of machine learning. But since most of you, I mean, how many of you have done any machine learning algorithms ever? Okay, I see 50% of the people have not done it. So today I'll start with basics of machine learning, which is required for you to go on and understand the contents. And we'll touch upon the first lecture. What do you record? I can wait this, no? And record. Okay, as I was saying, we'll start with the basics of machine learning. Then we'll move on to the contents of the first lecture that Andre Karpathy has read, K nearest neighbors and part of linear classification. Okay. Let's talk about. So I think most of you have written a program to classify odd numbers from even numbers. How do you do it? Can you speak a bit louder? I'm having a modulo operator. Okay. So essentially, if you think x is an array, I have 0 to let's say 9. What I will do is, if I iterate over this, if x of I modulo equals 0, that means this is even. Otherwise, it's an odd. So what we just did was, you converted this set of numbers into two different classes using this operator, right? Yes. So this equation itself becomes a classifier, right? So after performing this operation, your new x looks like 0, 1, 0, 1, 0, 1, right? If you plot those things on a graph, this is how it looks like. This is 0, 1, 2, 3, right? Now, what are you doing exactly over here? Is after you do this, you're basically drawing the line over here. Whichever falls above this is an odd number. Below this is
recording हो रहा है
right. You probably have not interpreted this problem as this way, but you've already built a machine learning, right? So that's it. This is the whole gist of the machine learning. What you got is a set of features. We call X as features, and our target was this 0, 1, 0, 1, where 0 encoded as even and 1 encoded as odd. So let me get some terminologies away. Right. So X is our input. Now, it contains, we say, m rows and n columns. In case of this, we had 10 rows, that is m becomes 10, and column we had only 1. So I can write X as this 0, 1, 2, 3, up to 9. So we had 10 rows, and the number of features we had is only 1. So each row had only one element describing itself, in which the set of features describe a particular input or a particular class. So let's take a look at the problem of logical OR. So how many of you are aware of logical OR operation? Everyone, right? So let's take two inputs, x0, x1, and what should be my output? If I have 0, 0, my OR is 0, 0, 1, 1, 1, 0, 1, 1, 1. This is OR table. Now, if I plot this in a 2-dimensional graph, I'll take 0 over here, let -1 be here, 1, 0. So the first point is 0, 0. I'll represent a 0 as this and 1 as plus. This represents 0th class. I can tell this as a 0th class and one class, right? And rest all becomes this. Right? Using this data, if you were to write an algorithm which can predict the correct value of OR, how can you do it? So, if you remember in the odd even case, we had data points like this. We drew a line like this, right? This was odd, this was even, right? Now, can you draw a line over here as well to segregate them? Yes. And can you tell me what can be the line from where? If I have something like a 0.5 over here and 0.5 over here. 0.5 to 0.5, right? This can be my divider, right? So, what makes a line? How do you represent a line in linear algebra or anywhere? Y is equal to mx plus c. Right? Y is equal to mx plus c. Can you tell me m and c for this? A bit louder. What is the value for m? -1. Okay. How did you calculate that?
y2 minus y1 divided by
Okay.
x.
If I say minus x, then what is the value for c?
0.5.
Right. Now this is my classifier. Right. So the terms we use for m and c over here is called parameters. The approach we just took is a parametric approach. We learned from data, we learned m and c from the data, that is, we learned the values of parameters through the data. This is called data driven approach. And using this, we built our classifier. So there was nothing you did, like you never set any of the values for m and c. You just learned it from the data. So this learning from data is machine learning. Now, if I change this to AND, this becomes 0, this becomes 0, 0. So, same problem, or let us have something. Now, only this point is 1. Other than that, everything is 0, right? So this should be my line. Similar to that, right? If I if there is a different set of data points, let's say I have bunch of positive class over here, bunch of negative class over here. So I would have to fit a line like this somewhere, okay, which can divide both the data sets. Now, when we let's take this data set for example. Let's assume this line is called decision boundary, by the way. If what is the equation for this? C0, right? Now I'm telling you, I'm talking about significance of C is equal to 0 over here. If I just consider y is equal to mx, what happens is your decision boundary can only rotate along this point, about this point, sorry, right? So if I don't have a C term, I cannot have any arbitrary line. So C, the intercept, is an important term over here. In machine learning terms, we call it as bias. Right? So these are the few quick terminologies I'm getting through. Okay. Let's talk about characteristics of y is equal to mx plus c. Now, this will always be a line in a Euclidean space. We are always talking about Euclidean space. By the way, if I talk something about Euclidean space, something jargon, just ask me what it is. You should be knowing these terms. When we say Euclidean term, in all, whenever we have a Cartesian coordinate, right? We have two axes and all are real number. That is called Euclidean space. If we plot these values over here, it is called feature space. Okay. Now, what are the characteristics of mx plus c? This will always be a line. Now, let's consider a problem of XOR. Now, XOR. Anybody remembers what is an XOR?
Inputs are not equal.
If inputs are not equal,
Output is 1.
right. Now we have 1 over here, 0. If I plot the same thing over here, now the 0 is this. So this is our XOR, right? Now can you fit a line over here which can divide both the classes? Like this?
Non-linear. It's a non-linear function.
So you cannot use y is equal to mx plus c to do this, right? Yeah. What if I added one more axis? Let's say this is my x0, this is my x1, right? Now 0. Let's take this as 0 itself. Now 0 is here. 0 is here. Now, wherever there is 1, I'll just add one more dimension to this. Let's say this is my other dimension, x2. Whenever the output is 1, if I just put 1 over here, I've elevated these things to here, right? 1 and 1 in the z-axis. So imagine just pulling these out of the boot. Now I can put a plane over here which can divide. That plane is y is equal to m x1 plus y is equal to m1 x1, sorry, m1 x1 plus m2 x2 plus 0. So if I add one more dimension, this is solvable. The problem is, how do you figure out what to add? So
that plane is that plane which is separating that z-axis.
yes,
One also.
yes. All your zeros are lying on the bottom.
One on the bottom and
The ones are in the z-axis. Just to make that problem concrete, let's assume we have this data set. 0, 1, 2, 3. Now, someone told me about nonlinear decision. This is again a nonlinear problem. We cannot have a single line to cut these data points. So what I'll do is I'll add this will divide. Okay. Now, what if I don't want a nonlinear boundary to divide this? What if I wanted to pull this out in another dimension and have a plane to its job? Because whenever we have nonlinear things, the equation for this is xy is equal to 1. Right? This is not a pretty equation because it contains 2 degrees. So whenever we have a linear equation, it is easy for us to do matrix multiplication and stuff like that to get a solution faster. Like, what is the polynomial degree for this? 1 and 1. 1 plus 1. So it's a 2 degree polynomial. Right? It's a quadratic equation. So we would always want to have linear equations. If you have linear equation, we can learn things faster using something called gradient descent, which is a universal algorithm. Right? Let's plot this. Now this is state x0, x1. So now we have 0, 3, 1, 2, 2, 1, 3, 1. Right? Now y is 0, 1, 1. So similar to XOR. Right? What if I took, let's take x not times x1, right? This becomes 0, this becomes 2, this becomes 2, this becomes 0. Now my new feature set is this, right? Now if I plot x0 here, x1 here, and it's not doing here. What happens is these 2 points 0, 3 and 3, 0 will lie over here in the bottom plane, whereas x1 multiplied it will lie here. So now I can fit a plane. Now if you crush this plane to the same direction, you will get xy.
You will put in 2 dimensions. Like
yeah, I have 2 dimensions. Now, if I look at from the above, in this from z-axis, it looks like a parabola.
Could you talk about like why having an extra dimension is still faster than like solving?
Yes. Now, what are the possible values for xy equals 1? I'll come to that point. When we reach gradient descent, we'll talk about it. I need to introduce 2 more concepts to go over there. Yeah. So, it's always this, right? We always think in terms of linear lines. It's always lines. And all our approaches are always linear. Whenever we have 2 for loops, it becomes quadratic. You always want everything to happen in a single shot. So that's the gist of it. We'll come to the So you understood adding a new feature over here. This is called feature engineering. So data scientists are paid for this. identifying how to add. Actually, data scientists were being paid for this. Right now, with the advent of deep learning and deep neural network, these sort of features will automatically learn from the data. Whatever we said, x0, x1, it's a quadratic term, right? So my neural network will start learning these combinations. We'll get to k nearest neighbor in a second. In that you'll see how even a simple algorithm can address these non-linearities without having to do much. So the key takeaway from this quick introduction is what is features? What are features? What is your target? Target is nothing but your y. It is also sometimes called labels as well, classes. And there is a term called feature engineering where we use multiple features, we hand tune them, and in order to address a particular problem, we'll create those features, and using that, we convert our problem from quadratic space to linear space. Right? There's a branch, I'll just answer the question. There's a branch of optimization techniques called convex optimization and non-convex optimization. The problem which you saw, this thing, is a non-convex optimization. Right? So if I convert this problem into another domain, this is called duality theorem. If I convert this to linear space, it becomes a convex problem. Now the convex problem are always learnable using gradient descent. Convex problem is nothing but you have a surface like this. You're trying to minimize it. Okay. Let me introduce one more concept. How many of you have taken mathematics as in your engineering or so everybody knows a bit of differentiation? Yes. Right. Now let's take this problem, y is equal to x squared. How does it look in a graph? Right? Now do you need a chair or something? You can sit over here. Now, I'm sure you have done this. How do you find maxima or a minima? So what you do is you just do dy by dx. Dy by dx is 2x, right? Now, if I want to find the minima or the maxima, what I'll do is I'll assign this to 0. Now, what happens is x becomes 0 over here from this. What this says is, for this curve, there is a maxima or a minima, which is at this particular point, right? Okay, how do you know whether it is a maxima or a minima? Okay. If I do d square y by dx square, it is coming as 0, right? Whether this is a maximum or a minimum? Oh, sorry, 2. Yeah. Whether it is a maximum or a minimum? How do you interpret this?
If it's positive, it's a minimum.
Yes, that's the definition people have given. How do you interpret this? Okay. Okay, let's take from this. What is this dy by dx? The amount of change in x results. What is the amount of change in y, which is resultant from the changes in x? Right. If I change x by one factor, 1 unit, y changes by 2 units. Now, if I had x is equal to 0, y was 0. Now, x is equal to now, if I change x is equal to 0.5, y becomes 0.25. If I take y over x or x over y, 0.25 by 0.5, 1 over 2. This is a 2-factor change that has happened, right? That's why if you plot the points, you always see the distance quadrupling. So what dy by dx is saying is, if I change quantity of x by 1 unit, y changes it by 2 units, right? Coming to this, now if I just plot this graph, now y is equal to 2x. This is a linear. What it says is, forget about, don't worry about this equation. Consider this as our first equation itself. Now, x, what it is saying is x is influencing y for 2 times every time. Now, if I differentiate this becomes a constant. That means this is a linear curve. Whenever this becomes constant, if this was another curve, once I differentiate, if this was another curve, that means it is another higher level term, right? So there is not much you can do about it after second differentiation. Now, if you have reached a particular value, which is a positive value, that means this is a positive one. That means this is a minimum. If it is negative, that is, if it was minus x square, if I had this, then it is a maximum, right? Okay, this was a quick detour. I'll come back to this.
Can you please explain a bit why it is minimum as why it is maximum? Like,
Okay.
to explain.
Now,
Interpretation of that D2.
no, this was 2x. So it's 2. Now, if I put, this is nothing but putting a tangent at this point, right? Now, where can you put a tangent for this line? The line itself is a tangent, right? If this angle if I had tangent over here, that says at this point, this is the value of the differentiation. If I substitute this, if I come over here, this is the minimum. Then again, if I move over here, it is moving like this. The direction of this is dictating whether it is a positive value or negative value. Now, if I move like this, if I have this curve, I would move like this. The clockwise and anti-clockwise is defined by the sign, plus or minus. Now the sign is positive, that means it is a minimum. If its sign is negative, that means it's a maximum. So that's how you do it. Now, again, we'll come back to this. The whole gradient descent is based on this, the direction in which it flows. In order to explain gradient descent, let's take a very popular problem, housing price prediction. Let's say you want to buy a house in Indranagar. This is the area, this is the price. You have a small house which costs around, let's say, 750 lakhs, and a large house which, say, costs you 100 lakhs. Now this small house, let's quantify the area. What is a typical small house area? 850, okay. 850 square feet. And let's say, let's double this, 2000 square feet. Now, I have a 1000 square feet house, let's say 1200 square feet house. What can be the price? Yeah. I'm not asking questions. If I plot area in the x-axis and the price in the y-axis, let's say 850 somewhere here, and 2000 is somewhere here, according to price. Okay. Is it visible? Now, the 1200, let's say it's coming over here, this point, right? How do you figure out what can be the value here? What can be the price for this house?
Draw line.
Draw a line, yes. Do a line. Now project this here. Hit this. This is the way you do it. Now you did it by using eyeballing. But your system can't use eyeballing. So what we do is, whenever we are given data, let's assume few more points just to make this interesting. What you do is you randomly start with a line like this, right? And see the difference in the prices, right? These are the errors from your data set. Now, if you just add them, let's say the error was even after adding all these deltas, you would want to minimize this error, right? This is okay. What if a point was here as well? Now this delta is negative. This is positive. Now if you just sum them up, it may so happen that these two cancel out. And according to this formula, you would say there is no error between these 2 points, right? It's not a good way of doing it. What you can do is you can take the absolute value of it and add that. If you do this, this error term is called L1 distance. Level 1 is line. So L1 distance is nothing but absolute sum of absolute errors. Okay. Now, if I plot the L1 here, L1 is nothing but absolute value of a particular number, right? Now, y is equal to absolute value of x. If I plot it, it looks like this. Any question here? Is it visible to everyone? Y is equal to absolute x is this curve, which is an inverted triangle.
Can you please explain it, this curve bit?
Yeah. Now take x is equal to 1. What is the value of y?
Plus 1.
No, this is absolute. If I take x is equal to minus 1, 1. Now x is here, minus 1. If I take x is equal to 0, y is 0. So this is the term. It doesn't matter what is your value of x, y will always be positive. And there is a deviation here. Right? Now in calculus, this is not this curve is not differentiable at this point. Because there is a sudden change in direction, there is a discontinuity over here. Okay, just a comment. Let's have this. Okay, this is one way of doing it. Now, let's take another approach. Rather than doing this, let's square it. Let's square the errors and then sum them and then take the square if needed, or just keep it. So, if I do that, my errors are nothing but delta e square, sum of delta e squares. Right? Now this is nothing but y is equal to x square. This curve is if I just plot those errors, this is the curve. This is differentiable. So I can ask a question, where is this error minimum? Okay, now based on this line, this is the line I have. If I calculate error and plot the values for those errors, maybe it was here. Now using this curve, if I ask for where was this, where is this error minimum, I'll just take a differentiation, dy by dx of this. It will tell me 2x. What this says is, at this point, this is the tangent, and this is giving me the direction towards the minimum point, minimum error. So what I'll do is, I'll just update my y's, that m and c's, with using these values to go towards this point. We'll get into the details of the algorithm later, but I'm just giving you the intuition. Now, if I update the m and c such that my line goes towards the minimum of the error, let's say it moved here. In this graph, it looks like this. I moved from this line to this line. Okay. Similarly, at this point, finally, I'll be fitting a line which has minimum error. So we took y is equal to x square as an analogy. Actually, it will not be exactly at 0. You need not have a zero error function. It can be somewhere here, somewhere. Right. So in order to reach this minimum point, we'll follow this. First, we'll calculate the error, take its differentiation. From the differentiation value, we'll get the direction towards which the line has to be moved. And using that, we'll update the coordinates, the parameters of the line, m and c. Now, we started with random m and random c. We are slowly updating it, so it will move towards a minimum point. Once it reaches minimum point, it will not wiggle. It will always be there. So this is gradient descent algorithm. This is how you learn parameters. I see a lot of confused faces. Any questions?
This is what used in regression techniques.
Any neural network algorithm or classifier, logistic regression, linear regression, and neural networks. This is how you learn.
Any parametric one?
Need not be. Yeah, maybe. There are some which we don't use this. There are some which are deterministic methods. LGBFS. This is a first order optimization. There is a second order optimization as well, which we can use something like a Newton's method. To find a square root of a particular number, you would use Newton's method. Look it up whenever you have to.
So any first order parametric model that can be
Yes, this is the universal learning algorithm. Now, the problem comes when you don't have this surface in a convex function. For example, if I have a function, if I draw a line between any 2 points and this line doesn't cross any other point on the curve, it is called convex. It is a bowl-shaped curve. Now, if I have something like this is a non-convex problem. This has 2 minimum points. So, gradient descent assumes there is only one single minimum point. Otherwise, what happens is, if you're here and you reach this point, and this is the minimum you had, you would always stay here, because if you move here, the error increases. So after a few iterations, you see error is not changing, and you'll stop at that point. Whereas actual error was here. Now this is called local minimum problem. There is another problem as well, something like this. If my learning curve is like this, the error is something like this. I'm here. After, let's say, 1000 iterations, the error is not changing at all.
constant.
So this is plateaued out. So you would you don't have forever to do this, right? You would limit at certain iterations, and after that you just stop and say this is done. This is the minimum. Whereas the minimum was here. So for that, what you do is there is something called momentum. You just boost something, like randomly you will jump over here and then try it. It can be both directions, right? If I jump over here, if this was the minima, it would go here. But since this is not minima, it would move slowly like this and suddenly move. And how much to update your parameters is controlled by some hyperparameter. See, two distinctions are: parameters are something you learn, hyperparameters is something you assign yourself. Now, the rule is, let's say m This is new M. This is your old M. What to do is you have a learning rate. Let's call it as alpha, and your gradient. The whatever differentiation we did, it's called gradient. This is the gradient. So what you're doing is you're slowly updating your parameters like this. This is nothing but the gradient from the error function. So this is how you learn. So M and C are updated like this. Now, if I keep this value alpha, let's say 10, what may happen is, I was here. I know the direction where to go, so I would take few more steps in that direction. If I don't use this alpha itself, I would have taken this long step. If I keep this as 10, let's say I jump over here. Next step, again I will take a gradient. Now, since alpha is 10, I'm magnifying my steps by 10 times. The given direction was here. Since I multiplied it, maybe it shooted over here. So I would jump over here. The actual point is here. Since the curve is over here, I would jump over here. Again, I would do the same thing. I would keep on jumping like this. So this alpha is very important. This is called learning rate. I would keep it somewhere like 0.01 or 0.01, something like that. Take smaller steps as much as possible. And not so small so that your algorithm will never converge.
So this learning rate is also this hyperparameter?
Yes, this is what you said.
But it depends on the sample, right?
Exactly. So I was showing something on the curve itself, right? So if I have this curve, I would have chosen different path. How steep is the curve?
How do you know that alpha 0.01 is the right curve?
That is where the data scientist comes in. So you would have to do something like a grid search. Grid search is like take all possible values, run your experiments, which fits the better. But there are a lot of research happening right now. There is a very new technique called learning rate finder. If you have heard of fast AI, anyone? Jeremy Howard. Okay, you should look it up. Fast AI is started by Jeremy Howard. He was the ex-president of Kaggle. Kaggle is again a forum where data scientists compete. So what he has implemented a paper. I will give you the links to the paper. It's not his work, but he has implemented learning rate finder in his library called Fast AI. What it does is it takes a sample, it takes your data set, and in a single pass, it will start increasing the learning rate and plots it as a curve. So till some learning rate, the error value goes down, and after that it shoots up. Maybe something like this. Now, this is the minimum that loss this learning rate could find. Right? This is learning rate and this is error. Now, after this point, learning rate started to shoot up. So what you would do is you would choose a value somewhere over here. Check out Fast AI. It's really cool. Yeah. So finding the learning rate itself was a big problem a couple of years back. You would run experiments a whole day to find out what is the proper learning rate, because your data set would be like huge, like 1 million pages. Just to run a single pass, it would take like 3 hours, 4 hours with multiple GPUs. Yeah, this is a very quick introduction to machine learning. I'll give you very good links which you can go through. Before we say, John Brown channel. If you want to have an intuitive understanding of any mathematical concepts, this is really this is really good actually. And I think he has a video on neural networks. Yes, sir. Yeah, this is very cool. I mean, he's very intuitive. He explains things in a visual manner. So have a look at this. And he talks about gradient descent in much detail and in a better composed way actually. So you can have a look at this. You don't need to take notes. We can post it. Okay, this is the content from CS231. This is Andekar Pathik's class. Okay. Now, okay. How do you do image classification? Any answers? Naive way of doing image classification. If I give you two sets of images, dogs and cats, and if you want to write a program, an algorithm, and to do a classification, what is your take on it? How would you do it? Non-machine learning. If you had to write hand code all the rules,
take out some features, color, texture, shape.
And can you give me a complete algorithm? Like, say, once you take the color, what would be?
Some of the discriminative features, identifying features that I'll identify first, and then such as the shape, size.
You understand, right?
Yeah.
When you say shape, how do you extract shape using your program?
So I would use 2D matrix
Okay.
of the image
Okay.
with dog one and then the cat one and then compare them. And if
How do you compare?
So matrix has a
Try to extract the edges and try to construct a shape
Okay.
and
Once you extract the shape, what do you do? So how do you represent the edges itself? It will again be a matrix.
in a matrix, yeah.
Okay. So that sentence itself, finding the edges, again requires another big program.
Another big program.
Divide it into very small bits,
Okay.
and then make it as a bag of cats and bag of dog. So with small bits,
Okay.
and then whenever an image comes, that will be another bag. Compare each and every bits, and the most number of bits will be cats or dogs.
Don't talk about bits, talk about as a pixels.
Pixels. So after you have broken down into each and every pixels,
So what you're essentially saying is divide the image into certain blocks and put them in a bag, in the sense shuffle them. Compare two bags of pixels. Now, what could be your comparison function?
normal RGBs.
Yes, you have RGB. Let's say you have 255, 255, and 000. How do you compare them? What operation do you do?
Similarity.
It's a vector. See, all these are words, similarity. How do you define it?
So if it is like RGB, that can be represented in terms of vector. Suppose.
Okay, let's say 255, 255,
Yeah,
000. So how do you say these two are similar or not?
So using some sign similarity or any kind of similarity function that
We spoke about L1 distance.
we can
And
use
the square root.
Square
Square root is called L2 distance. Can that be one? So to break this problem, what you're doing is you're taking two images, finding how similar are they. Right? Now, defining this function itself is the whole problem. Once you define that metric, the function, the output of that is just a number, and you can always do classification like this, logistic classification or linear classification, using those numbers. Right? Defining that function is nothing but extracting the features. Right? I'm transforming this particular image into this representation. this particular number represents that image. Right? So this is the essence of it. Now, using just the L1 distance. Now, an image is nothing but a matrix of values. It has three matrices: one for red, one for green, one for blue color. Right? Why is this a hard problem? Someone said use bag of pixels, right? Now, if I take pictures of dogs and cats with a similar background, right? Similar background, right? You won't expect the cat to be in the whole of the frame, right? Those pixel values, which represent the background, are not a distinctive features, right? It would work. Your classifier would work if the background was similar in both the cases. If they were in completely different background, that would not work, right? A simple negative, difference between the pixel values is not a good way of looking at it. So we need to go for sophisticated approach, something like find an edge data. Right? Do the edge detection and quantify that edge as something like into a shape. Shape, we understand shape. System doesn't understand shape. So quantify that as something. Right? We need to do the hand-tuned, we call it as kernels. Finding the edges is using a kernel. Right? You use a kernel and just place it over it. And if there is a gradient between edges, like whenever you have an edge, let's say there is this edge, you have zeros here. Let's talk about zeros and ones here, sir. And 1 over here, and again you have zeros. Right? This represents edge in your image. What you would want to do is figure out this pattern. Wherever you have zeros, 1, 0, that is an edge. Now we are talking about 1 pixel width over here. If you have a thicker edge, you would have 0, 1, 1. Right? So this is an edge represented in an image. So you would have a filter, let's say, let's take 0, 1, 1, 0 itself as a filter. I'll place it over here and then multiply them and add them, right? Or I would just take a difference and then add them. So if this is 0, that means it is an edge. You would move along this line and figure out the edge. This is a very crude way of saying it. The algorithm never works like this. So this is the intuition. So whether there is a cat or not, it can be figured out using the edges.
So is it like manual job or how are you going to do that? Because if you see here, these different pixels have different values. So finding a pattern will become much difficult in some cases. So how are you going to handle that?
The kernel creation of the kernel itself, it was manual until the deep learning came. The neural network's job is to find out these different kernels and extract numbers from them, which represents those shapes, those sizes, those colors into these numbers. That's why you call it as representation learning. Okay, deep learning, the essence of deep learning is just to extract good features. And once you extract good features, you feed it to logistic regression model, something like that, and then classify. Right? So, why is this a problem? Viewpoint variation. We humans understand this is a single item, right? This is zero. There is a scale variation. You can have the cat in the most smallest possible way in the picture, or you can have a zoomed in version of it. Right? Deformation. We can identify this as a cat. Now, if you feed in the cats which are standing up to your algorithm, it won't be able to recognize this as a cat because it is not learning like us. Right? This is an occlusion. You don't need to even mention this. If you search for cat woman, you don't need to. If you just show this picture, a kid would recognize this as cat woman because of the ears. Right? That is the most distinctive features. feature. Right? So our conclusion doesn't matter for us, whereas the neural network classifier would be affected. Elimination conditions is, for us, all of them are payments. Right? I can barely see the cat if they don't show me the face. I would never recognize this as a cat. It looks more like a leopard to me because of the background. Interclassification. All of these are chairs, but in order to feed this to a classifier, we need to have different variations. So I spoke about data-driven approach. We are never doing hand-coded rule-based programming. We are always feeding all the data to it and let the machine learn from the pattern. Okay, I'm going quickly over this. These content are available online, and there's a video to go along with this as well. You can go through that. So just we are using something called CFAR dataset. CFAR has 32 by 32 image. It has 32 by 32 into 3 pixels. That is 3072 pixels. And it has 10 categories. And we are trying to learn that. So any image classification task it goes something like this. It has input of images and has k different classes. Right? We feed it to an algorithm whose task is to identify discriminating features and understand the relation between classes and map those features. Right? And evaluation is once you feed in your data, you would want to quantify how good your algorithm is. Right? For example, if you're feeding cat faces, only cat faces, and whole of the dog, and try to do dogs versus cat, then it would perform really well because for cats you're only inputting faces, whereas for dog it has a body as well. Now, by testing, if you pass in the cat with the whole body, it would fail miserably because it has never seen the body. So we need to test our algorithms based on what we're training the data. So the training data and the other set, we call it as validation set, have to be in the similar distribution. They have to be similar. Then only it will work fine. Your model works fine. So that's how we evaluate. We'll get into more. So these are the 10 classes, and each is a 32 by 32. Let's take his approach. Rather than using bag of pixels, let's take him as it is, and take 2 images, and calculate L1 distance pixel by pixel. Right? If we do that, and once you have the sum, just add them. That is L1 distance. Now, when you have a training, when you have an image, let's say for cat, you have a representation image, and if there's a test image, what you do is you just take the L1 distance, and if that number is low, you get to decide what is the threshold. If that number is low, then classify it as a cat, otherwise classify it as a dog.
So here the L1 distance needs to be taken by doing that subtraction pixel by pixel.
Yes. Let's talk about pixel by pixel. This is not an algorithm anybody uses. This is just to give an idea how things work. Right? You understood the concept of L1 distance? Yes. How we are doing it? Okay, let's get into ESD. Now, this is our data. Okay. Now, if I ask you which class this mouse pointer belongs to, what would you say?
Blue.
The nearest points.
Blue. And how did you come to the conclusion that it's blue?
Nearest of the nearest.
Okay. You're can you explain me in a three-step process? Like, what did you do?
Distance from the place where you want to nearest color.
Nearest classes are like this. And how many data points did you take to calculate the distances?
That will decide, like maybe if I take 100 points nearest. So among those 100 points, majority of the
Okay.
points, whichever class they are belonging, so it will be.
That is k nearest neighbors. That 100 is k is 100. You're taking 100 nearest neighbors. What? If I ask you to write a program for this, what are the steps you do? Can you tell me each and every step? You have an image. Let's convert it into one dimensional, 3072 pixels. Now you have an image with 3072 length vector. Okay, and you have training set, which again has 3072 images. Pixel values and numerous images, and associated to it is your classes. So whatever you did was an eyeball, right? What an algorithm would look like is, you take a test point, that is the mouse pointer, and calculate element distance between every possible point in the plane.
So I can say whole array.
Whole data set,
Yeah, whole data set.
whole training set, right? Once you calculate that, now you have element distances for each point. Now, what you do is you sort them according to the least distance or the most similar. Right? Then, if you choose to select from 5 points, you select top 5 and see how many of them belongs to which class. Now, majority, if it says it's a blue class, you classify them as blue. So this is the algorithm. Now, for one test point, what is the complexity of this algorithm?
En, often.
Often, right? For one point, it was often. Now, if I have m data points,
M into N.
so they will keep calculating distance between every page, right? So this is n square. Now, what is the effect of k over here? If I select, let's say I want to know this point, the most point of variable, and if I choose k as the number of, let's say 10. If I choose 10 as my key, what I would do is I would majority take the vote of blue and it will be blue. Now, if I take only one point, if I put k is equal to 1, what happens?
So when I sort, I will consider the first one.
First one. Okay. What is the effect on the map?
So some cases I can be having 2 or 3 points that having the same value.
I think the shape will smoothen up as you increase scale.
Yes.
It don't generalize.
Okay. Yes. That's the effect. Now this is k is equal to 1. Now if you see this, for k is equal to 1, you have these islands formed. Would you consider this as a good classifier?
No.
Why is that?
It's overfitting the training data.
That's the technical term.
It tries to learn everything, whatever.
It tries to fit the data exactly.
How it is, it will learn.
And what is the effect
The failure
of it?
When
It's
it's
like by hatting whatever. It's not learning it.
Yes.
Not generalizing.
Now, if I have a different data set from a different, it would not generalize. So it's the word you're looking for is generalization, right? How do you make this generalization?
increase K.
Increase scale.
And why do you think that would smoothen out the curve?
Compare larger data sets. Like
Larger data set or larger data points? Okay. And why do you think comparing with larger data point helps?
because generalized compared to it's kind of mean.
You're reducing the variance in the decisions. By considering only one point, like it's like one of your friend recommended this app and we downloaded it. And it turns out to be terrible. Now next time you would be sure that you would ask a few more people before downloading an app or investing in something. Right? It's just as simple as that. You would want more data to decide on it, so that you would not have any bias from your data. So we say this has very high variance. The first k is equal to. Now, certain k is equal to 25 is a very smooth curve. And I would consider this rather than this. You still have a lot of islands over. Right? These are the practical things.
But can I take it to the other extreme? Like if we make it all the points are data.
So-
K is all the points.
If you select k is equal to all the points, what will happen? Just think about it.
I mean not all, but
If you consider it all, it's a very good question.
It don't learn at all. Like the learning will be very minimal.
So it's always in between.
Just mapping between the point and
It's like calculating the average at that point.
yeah.
So one other way of looking at it is if you are considering all the data points, have different weights. For example, wherever I have a nearby points, I'll take the similarity more, and wherever the distance is very large, I do not consider it.
So it will not distinguish.
Have a weighted distance. So the term we call it for is kernel trick. We are calling it as a kernel trick.
Kernel?
Kernel trick.
Kernel trick.
You saw SVN example, non-linear classifier we saw, extending into another dimension. What we did was we elevated the data points into some other space. We fit a kernel out of it. The kernel was x times y, or x not x1. So whenever you have a grouping like that, if you put a, let's say, Gaussian kernel, you might have heard about it, bell curve. If you put a bell curve around that data point, what happens is the nearby data points will be weighed more, and you would consider them more for your recommendation. It's like you consider your friend's recommendation rather than your acquaintance. So, a better classifier is now. Looking at this, what do you think the nearest neighborhood classifier is? Is it a linear classifier or non-linear?
Non-linear.
Are we missing on something like if you move those data? By scrutining it, you are losing lot of data points. No, you are not losing it. That's how you validate the accuracy. You don't want. See, once you fit your algorithm like that, you would want to test it on test data set or a validation data set. If that performs well, then you are generalizing it. Okay. So even I don't care if my training accuracy is, let's say, 90%, and my test accuracy is again 90%, I will be happy with it. Now, if my training accuracy is 99% and my test accuracy is 70%, it's a massive move. That's because you have formed those small islands. You have fit your data too closely to generalize. It's always a trade-off. Accuracy versus training accuracy and generalization. So, what is K here? Who is setting the K?
We should set the K.
K is a hyperparameter. And what do you think the parameter for this? K nearest neighbors? Do you think we are learning any parameter over here? No. This is non-parameter.
No.
Right? That's the difference. So,
I mean, but aren't we setting the K to minimize the distance? So
yes.
distance is a parameter.
But distance is not a parameter. distance is a metric.
Yeah.
Now, distance in case of let's say regression model we saw is L2 distance. That is a metric. Whereas the parameter was MNC. We were trying to learn MNC. So,
There's no functional form.
yes, that's exactly what I was talking about. So, in parametric approach, you would end up with an equation at the end. Right? In case of non-parametric approach, you will not see that.
Is there more kind of clustering?
Yes, it builds up to clustering. Since we have labeled data, that is, we know which class it is. For each point, it's not clustered.
We have labeled it.
Yeah, that's why we have colored. Yeah. So one good thing of doing, I mean, if you were to adapt to this algorithm, what you would do is you would have a way. The k is your hyperparameter. You need to set it. So what you can do is take a list of values for k and perform the same thing and plot the validation accuracies. And if you see this validation accuracy, now the accuracy peaks over here and it slowly reduces. So I would use somewhere over here. This region is a generalized value. But this is very bad accuracy anyways. 30% is way low. But it is better than random guessing. If you were to randomly guess something, you would be at 10% because you have 10 classes. You would predict everything as a particular class and you would be 10% of the time. So that is called base accuracy, base model. Predicting a particular class based on the data that is average or mean or number of classes is called base accuracy, base model. So I'll see the count of each class. Whichever class is highest in the data set, I would just predict that as my class all the time. I would be getting 10% accuracy. Okay, so this is a practical machine learning. Like once you are given the data, what you should do? Once you are given the data, you would divide it as test data and training, right? And you would ideally forget that you have test data. You will not look at test data unless you have finalized your model. Okay? You would take a split and keep it aside, or better give it to someone. Don't look at it. Okay? Next, what you do is this training data. What you do is you divide it into certain parts, like say 5 folds. Okay? You build a model on first 4 folds. Folds is nothing but part of the data. First 80% of the data you prepare a model and validate on fold 5. Similarly, you would skip fold 1, build models on rest of the folds and predict fold 1. So this is called cross validation. Okay? So you would build 5 different models here and see the accuracy and average the accuracy, and that becomes your average for that model. Finally, you would want to build the model on entire training data. This approach is taken only to decide what algorithm to choose on this data. Now, if I perform k-nearest neighbors and let's say logistic regression, and I will do k-folds cross validation. This is what k-folds cross validation. Now, k being 5 over here, 5 folds cross validation. If my mean accuracy for k-folds, k-nearest neighbor is 80%, and logistic regression is giving me 85%, I see that logistic regression is performing very well on this data, and this data, logistic regression is suited for this data, and I would choose logistic regression as my algorithm. So you would never discard this fold 5 or the left out fold in the final model because data is very precious. You would use it. But you would never include test data in your model.
So, like, when suppose multiple algorithms are there, so first I'll keep aside the test data,
Yes.
and then only I have training and validation that data. Training data. So I'll do that cross validation.
Yes.
And then I'll suppose 4 algorithms are there. train the model, and after that, like suppose I get algorithm 2 that is giving the best mean accuracy. Then again, so for that like algorithm, I'll get the parameter values and everything. Okay. So now like
No, you're not getting the parameters. So what you're saying is, for this data, this algorithm performs better.
okay, so now again, like I get the optimum algorithm. So then again, I'll build the final model on the entire training data.
Yes. You build the final model on the entire training.
So when
the test data then?
Final
Test data
testing,
is just
final
to
testing.
find out what is your model's performance. That's
But
it.
if we have already selected an optimal model, what is the use of test data in that case? Because you have already
You
selected.
never chose the optimal model in cross-validation. You only chose the optimal algorithm. Which algorithm to use is found out using cross-validation. Once you figured out what is the algorithm, you train it on training data, right? And you predict on test data to evaluate your model. If you include test data also in your training, what happens is it would overfit on the particular data set, the whole data set, and it will perform really well. But once you have actual real-time data coming in, it will not perform well.
So the optimal model parameters, suppose finally logistic regression is giving the best on the training data among four different algorithms. So now in logistic regressions also, the parameters I have to finally I have to decide, right? So that
You are not deciding any parameters. You are only deciding on hyperparameters. In logistic regression, you do not have any hyperparameters. Okay. So if you are selecting a particular value for a particular variable, that is called hyperparameter. Now what you learn based on the algorithm is called parameters. So that learning happens on the whole of the training data. Right?
So to learn the hyperparameters, we use the test data for grid
To learn
search,
the hyperparameters, you use cross-validation.
cross-validation.
Yes.
So
But
let's
you
say
said
I
that
have.
we use different models like logistic regression, ANN, or
Yes, yes.
whatever. So
For-
there we are using different
There are two
models
things over here.
itself.
One is algorithm, right? And algorithm, if it is controlled by a hyperparameter, we need to look at that as well.
Learn
Right.
hyperparameter.
Now let's say I'm using two algorithms, k-nearest neighbors, and another one is logistic regression. Logistic regression do not have any hyperparameters, so that will be only one search for. I'll use k-folds validation on logistic regression, and I'll find out the accuracy, right? For k-nearest neighbors, let's say I'm using let's say 5, 10, and 15 are my keys hyperparameter. For each hyperparameter, I would run cross-validation, right? And find out the accuracies for 5 nearest neighbor, 10 nearest neighbor, and 15 nearest neighbor. And on that, I'll see the mean accuracy for all four of them. Now, let's say my 5 nearest neighbor is performing really well than all the other. I would
Then
choose
all
5
the-
nearest neighbor as my algorithm. KNN as my algorithm and 5 as my hyperparameter. And use that to train on the whole training data.
But if we are selecting the algorithm based on training data, what if that algorithm does not work well with the test data? Shouldn't we,
No.
like it might give a high accuracy on the training data?
So test data is something we say that is never given to you, right? Test data is actual real world scenario. We are hoping that it will work for you. Because you cannot simulate the real time data, right? Like let's say what is housing prices. So someone is fixing the housing prices. He has control over it. He looks at a lot of other parameters and then fixes it. Based on the data, you are trying to learn what he's going to think in the future. You don't have access to the future data. So that's why what you are doing is you're keeping aside part of the data set as the future data itself and trying to evaluate that as your accuracy.
Okay,
And
so
you're
the final
hoping
accuracy which we will say that my model has is
It's
based on the test data.
Yes.
So that is only to finalize the accuracy level of my model.
for evaluate your model.
Evaluate my model.
Yes.
So the model is actually selected based on
Cross-validating.
yes, and the accuracy evaluation is based on test data. That is the use of test
Models
data.
evaluation is based on test data, right? Algorithm picking and hyperparameter picking is based on training data using cross-validation.
So one more thing, so as you said, suppose there are two algorithms, one is logistic regression, another one is this k-nearest neighbor. So hyperparameter is there for k-nearest neighbor because that k is a vector parameter. So now again, so it becomes twofold actually. So among the logistic regression and so in the k-nearest neighbor, so you might find different k values, hyperparameter values. So in the k-nearest neighbor, so what would be the optimal value of the hyperparameter that you can do by cross validation?
Yes.
So then suppose for the k-nearest neighbor, you are from that cross validation you come to know okay, so 7 might be the best hyperparameter.
Yes.
So now in k-nearest neighbors with 7 hyperparameter, that is the best one. Now I have logistic regression. So to select between those two, so
Why do you need to do it in the two different stages? You can do everything in one stage, right? For k nearest neighbors, then move for different values of k and record your accuracy. So logistic regression again done the same thing in record your accuracy. Whichever is the best.
So those things, there's algorithm selection that needs to be done on the
Cross
validation.
Algorithm selection and hyperparameter
Parameter selection. And finally, the
model reporting accuracy is based on
test data.
So to understand what cross validation means, it's not only the accuracy part, it is also a lot of other features. Assuming the data to be proper, assuming your input values to be accurate. So there are many things that are actually checked in the cross validation.
Yeah.
If you really want to have a look, have a simple regression, linear regression example, then there are many good in sklearn itself. There are many good examples of cross validation for linear regression. Then you get an understanding of what they are trying to say. So what he is saying is not the accuracy only. It is a set of input parameters that you assume to be accurate in order to determine the algorithm to be run, or a model to be run. That's what he is saying.
You can algorithm selection and managing.
Yes, that's where the human comes.
That's where
That's where we are looking for your
visual intelligence.
There is no intelligence over there. Now there is a method which decides neural network structure based on the data. It learns to define its own neural network, but that's in very nascent stage.
I was reading a paper and there was an auto ML library.
That's just research. Whatever you're doing, you're just doing. You just automated the process. That's it. But nobody uses that because this is where the human knowledge comes. Right? Yeah, self-learning. I forgot the name. I'll search. Just ping me. No. PathNet is again, it's learning multiple tasks in a single day. Yes. That is PathNet. Let's not get into this. You can talk to me later because people will. Okay. Okay. If I have so what is the difference between a parametric approach and a non-parametric approach? For parametric approach, you will end up with y is equal to mx c sort of equation. Once you have that equation, to predict on the test data, you just have to run through the equation, right? For non-parametric approach, you would have to run the algorithm every time. So in here, for k-nearest neighbors, the training is nothing but to learn the k. The learning the hyperparameter was your training. When you have a new test data, you would again do the same thing. Or so non-parametric approach are not reproducible. If I have a different starting points, I would end up with different schemes. Whereas parametric approach are reproducible. But you can have reproducibility based on type of random seed you can set. But inherently they are not. Because the random seed we set in inherently is not random. You're always getting the same sequence again. So that's what. You end up with an equation in case of parametric approach. Once you have the equation, you just run your values through. And that gives you the prediction. Whereas non-parametric approach are very computationally intensive. For every data point you would have to do the same algorithm. Right? For k-nearest neighbors, you would have to again run the same whole algorithm. Yeah, pros and cons. Like, would key nearest neighbors work on this? They're all same units, right? If you ask a human, the person who's there in the city, on the same, it ideally should be the same. Why would key nearest neighbor fail with whatever approach we just did? The distance is L1 or L2, whatever it is. Sorry?
It will give a single class class.
Okay. Now, would it classify this as a single image? No, right? Because the original image. Now there is shift in the values, and we are taking pixel by pixel distance.
Yeah.
Now, the part of the gray here is seeing black. Now all of your distance metric is messed up. If there is a variation in the image, your algorithm will never. And if there is a patch over here, if the person is wearing an eye patch at a goggle, right, it will not work. And if the lighting conditions are not similar, it will not work because the pixel values change. So you can easily see this will never work. Yeah, this is just plotting based on the A2 distance. This is an algorithm called DC, we learn about it in later classes. If I just take the A2 distance, then this is how it classifies. Yeah, this is a k-nearest neighbors. Would not use this in any practical approaches. This is the important. Any questions on k-nearest neighbors? Again, you have to go back and read this. Right? You go to linear classification. Okay, this is a very old article I wrote from my institute, HandOn Labs. I share this. Let me go through this. So, how many of you watch football? Any avid fans of any particular club? Who's Liverpool? We'll never walk alone. Okay, IPL teams, any favorites? Since I'm in Bangalore, I'll go RCB. Actually, this was written right after the RCB final or semi-final. So imagine you have two teams, maybe for it. You can choose your favorite team. Now, just before the semi-final, this was the statistics. Now, Team A and B has faced so many games, okay? And since Team A is my favorite, I have a bias to this. Okay? That's one thing. And out of all the games Team A has played, it has won 65%. Right? And B has won 70%. Okay? And out of all the finals A has been in, it has won 50% of the games. And out of all the games B has been in, it has won 64 times out of 100. Right? If I ask you which team will win based on this data, what would be your prediction? You're betting on it. So even if you're a fan of A or B, imagine your money is on the line. And what would be your prediction?
B.
B, right? And what was the deciding factor here?
Finals and wins.
So there is a win percentage, there is a win percentage in finals. How do you weigh both of them? What was your deciding factor?
Higher weight.
Wins and finals.
Finals. Your deciding factor was finals.
What is the bias?
My favorite team is A. That was the bias. I have a bias towards my favorite. Or you.
No, I mean in the model or whatever predicting how it is.
The bias was the C term, visible time expression. Which will come to. So you have a bias towards. So no matter what your statistics is saying, I have a favoring towards this particular team. I would want this team to win. If there is a 50% chance of winning, then I would definitely go for team A because of the bias. That's exactly what it is. Now, if I say the final was in Team A's home ground, and they have won last 10 matches on a draw. Okay, and Team B is again not in home, can't be seen, right? They have won 10 out of 7, 7 out of 10 matches. So now your data looks like this. Which team would you predict?
I won't predict. There is no probability.
So what exactly did you do in this whole process?
Home advantage.
Yeah, the form and home advantage took your decision on it. But what was the thing you did in your mind?
Importance.
Weightage for each feature. And what was this weightage like? Like if you were to formulate this as an equation, how would you formulate it? Would it be like this? W being the weights. Now, I have a bias versus how much of the bias to consider is qualified by W bias. What is the win percentage? Detected in W win, the weight. Similarly, you have everything, right? If I put that in an equation like this, I get this at the value. According to these weights, the score is 0.83 for team A, 0.408 for team B. The weights I have chosen is this. Bias weight is 0.1, 0.2, 0.2, 0.3, 0.2. This is arbitrary weight. So, for this equation, what are the parameters?
The weights.
W, the vector of W is a parameter. Right? X is given to you. Right? So, according to that, 0.83 is the score which is given by this particular equation for team A. For team B has 0.4. Now, if I take the odds ratio for this, A is twice as likely to win than B. So, this is linear classifier. The weights are parameters. It will be in the form of y is equal to mx plus a, where m and x are vectors, not scales or particular single value. The reason I say vectors is features can be n number, right? So simply put, I suggest you to read. So that is a simple introduction to linear classifier. I'll share it. So, looking into that particular problem, this is the form of the equation, where W is a vector of values. So, Wxi plus B was your form of the equation, right? Now, can you extrapolate yourself from y is equal to mx plus c to Wx plus b? Now, W can be a matrix, W can be a vector. I'll get into more details. Okay. Now, based on your training data, each class has its own weights, right? So you have 3 classes. So you have 3 rows in W, and you have 4 features here. So you have 4 columns. So W will be in the shape of number of classes times number of features. Any questions? Now you have input vector. What you do is W times X, dot product of W and X. You take this row, multiply it, and there is a bias term for each class. Right? You cannot have multiple favorite teams. Each class.
Can you explain this case a bit? Can you please explain this one?
Now W is the weights, right?
It's chosen by
It is learned from the data. W is the parameter. Okay, let's say you have learned this. Okay. For each class, there will be different set of W's, right?
But until linear, let's say for linear regression, for each parameter we just have one weight.
Yes.
But this is for
not linear regression, logistic regression.
logistic.
Uh,
Logistic regression will have.
you read through the article, you understand. Actually, it
Okay.
is logistic regression.
Okay.
That article you just
Yeah, we will add it to the. If you have one, let's see them in terms of neurons. Let's say you have X coming in. You have a weight associated with it. Let's say W. Right? And there is a bias term also. Let's say there is a bias term B over here. And there is the output Y. What it does is W times X plus B. Right? Now here W is a vector. X is a vector, W is a vector, B is a scalar. Right? W dot X gives you a single number. Right? You multiply every component and add. That is a W transpose X. Since this is a vector, we write it as W transpose X. Right? Now, this is for in one, let's say. Let's say I have three classifiers. It will have W1, W2, and W3. And I'll use one more classifier over here. It takes the input W's and it will have its own W. What it does is X times W plus B, X times W2 plus B, X times W3 plus B, and it goes here. And this here, the output of these becomes features to this particular classifier. So this stacking of them is nothing but neural net. What can these be? B value. B value is also learned. W and B are parameters. Those are learned using gradient descent. Okay. So here, the structure of my weight matrix is 3 by 4. Now 3 is the number of classes, right? 4 is the number of features. Okay. And
so for each of the classes, the feature weights are different.
Yes, it has to be, right? In the end, you would predict whether this is a cat class or not, whether this is a dog class or not.
So give an example, like I mean, suppose for dog, like the 4 features are tail length, body length, body weight, and leg length, and then like for each class you will have separate weight. For dog, the tail length is higher, you will give more weight to the tail.
Yeah.
That way. So 3.
So yeah, that's what. Once you do Wx here, you would end up with, when you do M by N into N into P, you will get M by P, right? Matrix multiplication, you will get 3 length whatever. And this you add the bias to it, and this is your scope finally.
And one more thing, like for each of the classes, equal number of features will be.
Yes, the features are fixed. Right? Classes do not have features. The object or the row has so many columns. Those are the features. So if you do that, for each class, now what you did was you learned 3 classifiers. Yeah. Right? For 3 classes. Whether it is a plane or not, whether it is a car or not, whether it is a deer or not. This is multi-class classification. The first row, the weights, are for airplanes or whatever, the class one. So each equation gives you a line, right? Y is equal to mx plus c. So those are plotted over here. So since there were 3 classes, there were 3 classifiers only. 3 classes, 3 classifiers. These classes are like whether this is a class 1 or not, whether this is a class 2 or not. One versus the rest, right? So what you do is finally once you build this, if this particular class falls onto left side of the particular plane, then it is this. Yeah, just by template matching those weights. This is the average car looks. This is how average car. This is what your linear classifier has learned. So for a car classifier, if a car matches this template, this is the template which it has learned. If it matches this template, then it is a car. Otherwise, it is not. You can see this is already not a good classifier. If car was shifted out, it won't predict well.
All the perspective versions of the car are just.
Sorry?
All the perspectives of the car. You can have millions of perspectives.
No, what this classifier has learned, it has learned a template. Now, this we have 3072 features, right? The number of weights, we are weighting each and every pixel and then classifying it. The number of weights is also 3072. Now, if I reshape this 3072 into 32 by 3, I'll get an image, and this is that image.
There is one perspective.
No. That's exactly what I was saying. Linear classifier will not be able to work fine. So how I got this image is through this. Once I learned those W, I transformed it into this particular image. This is the perception of a car according to that classifier. This is one of the content PDF on my machine. Okay, let's say we are classifying whether blood pressure is high or not, and this is a systolic blood pressure. Now, if it is less than 120, it is considered as low blood pressure. If it is more than 120, it is considered as high blood pressure. Now, if I just predict y is equal to mx plus c over model, that would fit a line like this. Right? Mean of this and mean of this. It would go simple. Now, only one of these 2 points, two of these 2 points are correctly classified. This is why you cannot use linear regression for classification purposes, because it gives you y is equal to mx plus c. Y here is a continuous value. It is not telling you whether 0 or not. Okay? Now, all these are errors. So instead, what we have to do is we have to fit a function which is a stepwise function, something like this, right? If we fit this, then we are good. Like we are correctly classified. It's like in this dimension, I'm putting a vertical classifier, learning. So we can, but this function is not differentiable, right? It breaks at these 2 points. So we cannot learn the parameters from gradients. So what we do is instead we put in a smooth curve like this, right? This curve is called a sigmoid curve. Okay? So the equation for the sigmoid curve is this: 1 over 1 plus e to the power minus x. X is your features, or what mx plus c. X will be replaced by mx plus c. Okay? Now, what are the different shapes of the sigmoid curve? If I were to manually fit the sigmoid curve, I would change those mx plus c. Y is equal to 1 over e to the power 1 plus e to the power minus of mx plus c is my equation. This is my equation for sigmoid curve. Now, if I change m is equal to 10 and c is equal to this particular value, I get this very steep curve. And if I keep on changing the values, this is how sigmoid curve varies with it. Okay? Now, this is exactly what we are trying to learn, the different values of n, for which particular value error is minimized. If I perform a gradient design and have an animated version of it, this by varying m and c, this is how we get the curve. Right? So this is logistic regression. So once you have y is equal to mx plus c done, what you do is you pass it to a sigmoid function, sigma of whatever it is, and learn that from the gradient design. Once you learn that, you will get this curve. And basically what you are saying is, this is my curve, I will have a threshold at this point. If I put a threshold at 0.3, let's say, I will be misclassifying one of this. If I put it at, let's say, 0.87, I will misclassify this. Now, you should understand the threshold is at here, in the vertical axis. You decide a value over here, which would in turn give you a decision about your value. Ideal value is threshold 0.5. It will divide. Yeah. This was animation. So that works. Sigmoid works well. The properties of sigmoid function is sigmoid of x is always between 1 and 0. So you can interpret this as probability, right? When you have multiple classes, what sigmoid gives is whether this particular number, it transforms a particular number into 0 to 1. So when you have multiple classes, let's say you have 2 classes or 3 classes. In case of 2 classes, it's good to know whether this is this particular row is belongs to this class or not. I can represent it in a single number, like 0 or 1. Whereas in case of multiple class classification, you would have 0, 1 and 2, right? Now, for 0 you would have to predict, for 1 you have to predict, for 2 you have to predict. Now, I cannot have 0.9 over here, 0.8 over here, 0.7 here. It is not interpretable. So what you do is you normalize this, right? You normalize this to add up to 1. The way you do it is using something called softmax function. Okay? Yeah, this is the softmax function. You take a vector, you raise it to exponent of this and take sigma. Whatever vector you have, just take the exponent of it and then divide by the sum of the exponents. This will make sure the values are between 0 and 7. Okay? Now these values will be converted into probabilities. And whichever is the maximum, you can choose that. So we are just bringing everything in a singular scale. What we want to do is, on whatever class we are confident, I want to elevate that probability to as high as possible. Right? Whenever a class is, for this class, I'm not confident, I want to suppress that as much as possible. The nice function, the nice feature of exponent is, it is something like this. Whenever the values are less, it shrinks them down. Whenever the values are high, it elevates them. So I'm just making, when we do the linear scale, it is called linear scaling. If we do the linear scaling, the distances are kept in the ratio, linear ratio. When we do, say, softmax scaling, they are in the exponent ratios, so that we will be more confident on it. Now, if the values are in the range of very similar to it, you are not confident, and that will be reflected in case of softmax.
Different from one versus all.
Sorry?
One versus all.
So it's not different at all. It's just a new way of saying things. Now, I can even see this 0.9, 0.8, 0.7. I can choose 0.9 as my classes, but it will not tell you how confident is my classifier because everything is at a different scale. So you can't say I'm 90% confident that this is class 0. Right? It is not interpretable. In order to make it interpretable, we are moving this to softmax. So you can just do whichever is the maximum. Yeah. So key takeaway today is you would have a feature X, and you would to fit a model something like y is equal to mx plus c. Now y is equal to mx plus c is a linear function. You cannot have a non-linear surface like this. In order to introduce non-linearity, you would pass it through a non-linear function, something like a sigmoid function, right? Or a softmax. It's again a non-linear, because it is stretching things in a non-linear fashion, and use that for your classification. So this is the holy rule of internet. What you do is you fit a curve which is called mx plus c, assume mx plus c, and pass it to a non-linear function, and that becomes your classifier. The way you learn it is based on gradient descent, which uses gradients to follow the error surface to the minimum. Sorry, we didn't have time for hands-on. If I'll post the assignments as well for the CS231 in assignment. It has instructions how to get started. We will have to fill in the code blocks over there to understand what it is required, and we have built all the things which are required for the assignment. Calculating L1 distance, L2 distance, and softmax and softmax. We can do question 1 and question 2. Anyways, all the details will be published. Just follow that. Let me know if you have any questions. I think we are done.